Hello, everyone, and welcome to this week's SEDS Online webinar. As always, we'd like to thank our sponsors from IAS, which allows us to offer all of these resources free of charge. This includes recorded lectures, the learning tools, and even virtual field trips. So make sure you take a look at the website to see all of this new info. Today's lecture is by Drs. Frank Peel and Jillian Apps, who are research fellows at the Bureau of Economic Geology in Austin, Texas. Dr. Peel got his master's from the Imperial College London and PhD from the University of Oxford. His research interests are in all aspects of salt tectonics and structure and the interactions between salt and stratigraphy. And Dr. Apps received her master's from the University of Cambridge and PhD from the University of Liverpool. Her research interests focus on deep water turbidite stratigraphy and reservoir variability in structurally active basins. So thank you very much for this presentation, and I'll give it to you guys.
Okay, thank you. So today I'm going to show a Jurassic Lost World. And what this is there's a landscape that's been buried underneath salt, which is effectively transparent, and is preserved like a fly in amber. And we can see all the details on that surface that represent the day before the basin flooded and the salt was deposited. And it, as well as being beautiful, it tells us a great deal about the nature of the basin. So I want to thank, my co-presenter here, Jillian Apps, and TGS for permission to show the data. I'd like to remind people not to do any recording of the images, please. TGS have allowed us to show this as part of the AEPG Salt Basins Technical Interest Group, but on condition that the seismic images are not recorded. But feel free to enjoy them as they go past. So I'm going to start off by doing something I hope nobody's done before in this. I'm going to tell the entire history of the universe. So imagine, if you will, that the humble sheet of toilet paper you see before you represents 20 million years of geological time. At that rate, it only takes 3 rolls of toilet paper to take you back to the beginning of the universe, the Big Bang 3 rolls ago, 13.8 billion years. Our Milky Way galaxy formed some way into that first roll, but it didn't look like it did today. It was a roundish blob of stars until a galactic collision occurred, forming the spiral arms of our galaxy and a flurry of new star formation. And our solar system formed 4.567 billion years ago, just at the end of the second roll and the start of the third roll. And we are here. So these 3 rolls of toilet paper represent cosmic time. That's the entire history of our universe. So let's look in more detail at that last roll. So 1 roll of toilet paper represents the entire history of the solar system. 230 sheets. Let's roll them out and see what happened. So our solar system formed at the beginning of the first sheet. Shortly thereafter, the Earth formed 4.54 billion years ago, but it was a very unpleasant place. Magma oceans to start off with, large bodies coming in and colliding with it, asteroids, meteorites, and even the occasional medium-sized planet came in, one of which 4.53 billion years ago formed the moon to completely sterilized anything on the Earth. The first evidence of and this was a hellish time, you can imagine. So this period is called the Hadean, which is fancy speak for hellish. First liquid water probably formed about 4.4 billion years ago. And probably life first formed shortly thereafter, but all the time, bodies are coming in, crashing in, the Earth is getting sterilized again. So maybe life formed many, many times. The first evidence of life we see 4.1 billion years ago, chemical evidence, that is, not fossils, but it's having a hard time until 3.85 billion years ago, the end of the late heavy bombardment. And finally, the peaceful Archean era, no more major bombardment. The first fossils that we found 3.5 billion years ago, stromatolites. Photosynthesis starts, and it starts producing oxygen, but it's absorbed by oxidizing all the reduced material in the atmosphere and in the oceans. Mars freezes over about here. Finally, the oxygen builds up. You get the Great Oxygenation Event 2.4 billion years ago. Now that was good news for us because we like oxygen, but it was very bad news for almost everything living at the time because oxygen was poisonous to it. Nonetheless, complex cells form about here, multicellular life, the Cambrian explosion, dinosaurs, mammals, and finally us. So that's planetary time, the entire history of the Earth. Let's look at the last 50 sheets in more detail. For most of us, this is geological time because most of the rocks we see fall in this last billion years. But of course, geology covers the whole history of the Earth. So here we have the Proterozoic, the first animals, and then the Paleozoic and all the beautiful trilobites, fish, corals, land plants, amphibians, reptiles, dinosaurs, mammals, and us. Those are good things. Bad things also happening, all these red arrows here. The Earth freezing over at least 3 times. Mass extinctions here. The great dying at the end of the Permian, the Chicxulub impact here, and the extinctions that we are creating ourselves at present day. So that's geological time. Now let's look at one last sheet. We are here at the end of the last sheet. This is human time, the last 20 million years, because our ancestors, the hominids, formed in the middle of this sheet. Our more direct ancestors and things that looked more like us, Homo habilis and Homo erectus, and we started making stone tools and lighting fires. Homo sapiens appears here in the last ½ millimeter of the paper, 100,000 years ago. That's human time, also geological time. But if you want to see history and archaeology, the last 10,000 years, you've got to take this toilet roll of time and turn it on edge like this, because all of recorded history and archaeology fits in that last 1/20th of a millimeter. So let's zoom in on that. And here is an SEM image of the edge of a sheet of toilet paper. I think it looks frightfully uncomfortable, I have to say. But nonetheless, let's put history and archaeology on there at the same scale. So here we have the Neolithic, the Bronze Age, Stonehenge, the Roman Empire, the Norman Conquest, and the internet, and us. We're just a thin skim on the top of this toilet paper of time. So that's to give you a feeling of the difference between historical time, archaeological time, geological time. Where is this all going, and why the hell am I talking about this? Well, let's look at some rocks. South coast of England, the White Cliffs, 100 or 200 meters of chalk. This is definitely geology, and it took geological time, maybe 20 million years to deposit. So we're going to be looking at a formation called the Louann Salt, which is maybe 20 times as thick as these cliffs. So did the Louann Salt, which is a very thick deposit of rock, take geological time? Was it many millions of years to form? Or is it just possible that it could have formed very, very fast in geological terms, more like historical or archaeological period of time? Well, let's see. The Louann Salt is very mysterious. Some things we know about it. We know where it is. It's in the Gulf of Mexico, here between Mexico and the United States. Geologically, it's here. This is the pink Louann Salt in the north and the Sal de Campeche down in Mexico. It's present day. But back in the mid-Jurassic, that was all one basin and one continuous salt. The Louann Salt was deposited as Pangaea was breaking up. Laurasia to the north, Gondwana to the south, and a series of rift basins coming across what's going to be the Gulf of Mexico in the late Triassic. As the plates pull apart, those rift basins widen throughout the late Triassic and into the early Jurassic, and the waters start breaking through from the Tethys, and we get salt deposition in this bit of the central Atlantic at times. And sometimes maybe the water comes through into the Gulf of Mexico. The rifting propagates down to the south about 180 million years, and things change, and Yucatan starts to rotate, opening up a Caribbean, Proto-Caribbean basin, and a change in the Gulf of Mexico. Finally, at 170 million years ago in the Bajocian, the water connects through from the Atlantic Tethys, through the Proto-Caribbean, into the Proto-Gulf of Mexico, and the waters bring in the salt and the deposition of the Luann Salt at 170 million years ago. In chronostratigraphic terms, here's a stratigraphy for the northern Gulf of Mexico. And we can see at the bottom of this, the salt, the Luann salt, which we now know is Bajocian, thanks to some brilliant work done by Andy Pullum, who used strontium isotopes to date it at more or less exactly 170 million years. A brilliant bit of work, since published by others, but let's recognize Andy Pullum for doing that work. So we know the salt is deposited from evaporation of seawater, but there's a lot of things we don't know. How deep was the water in which the Luann was deposited? What was the mechanism of salt deposition? Was it shallow water evaporation like in a sabkha, or some kind of deep water precipitation? And how long did it take? So these two cartoon sections represent two end members. At the top, a conventional model, conventional wisdom is that the salt was deposited slowly as the basement subsided, and it was deposited in shallow water over many millions of years. And this is the general consensus. An alternate view, shown at the bottom, is that there was a deep hole. Let's wait for this to begin. There you go, a deep hole. And it sat mostly empty, and then the water came in and the salt was deposited very fast over maybe a period of thousands of years. And that's definitely a minority point of view. So let's look at the evidence either way. What would we normally look for the evidence? Well, fossils. But the Luann does not contain any fossils. How about interbedded sediments? There aren't any in the Luann. How about evaporite sequences that are known as Siglio sequences? Again, there's none in the Luann. If you know the pre-salt environment, that tells you a lot about the salt environment, but we don't know the pre-salt environment for the Luann, so we're kind of stuck. So for example, in the Zechstein, this is a schematic, and we know that the salt, the halite, is interbedded with other cycles of carbonate and anhydrite and shale. We can't tell much from looking at the salt, but we can tell a lot by looking at these other sediments. So you can tell where was shallow water, the shelf edge, the slope, the bathyal conditions. And from that, we know the shape of the basin. And from that, we know the environment and deposition of the Zechstein salt. But we can't do that in the Luann because we don't have those cycles. So what are we going to do? Can we use modern analogs? So, for example, the Dead Sea. The Dead Sea is a great place to go. You've got modern day salt deposition in deep water and in shallow water, but it's not a good analog for the Luann. It's way too small. It's in a different tectonic setting, a different type of water supply. The water for the Dead Sea comes down the Jordan River and it's fresh. And you simply cannot make a salt supergiant like the Luann in the Dead Sea. How about modern sabkhas like this one in Abu Dhabi, shallow water or continental conditions? But these are too small, and the evaporites they form don't look anything like the Luann. They're a different tectonic setting. And again, they can't generate a salt giant like the Luann. Here's another sabkha from Tunisia, during a period of salt deposition and during a period of water fill. They're very beautiful, they're very informative, but they really are not a good analog for the ancient supergiant salt deposits. So why is this? Why is the present just not a good key to the past? There are no modern analogs. There's several reasons for this. First, the modern climate of the world is wrong. Our world outside this window I'm looking at now is beautiful. It's anomalously cool. But in contrast, the Permian and the Triassic and the other periods of salt deposition typically were really hot, unpleasant times. Also, many salt supergiants form at a time of supercontinent breakup or ocean closure, like the Messinian. And we're just not in that tectonic setting in the world. Finally, salt deposition tends to be very rapid and very brief. A short period of time in a very long history of the world. And we would be very, very unlucky indeed to be living during one of those periods. And I say unlucky because salt deposition times are it's a very extreme condition. It's a very unpleasant. We would probably not live. We would probably die. So let's look at the evidence of this lost world of the Luann. So, as I said before, we'd like to make some inferences about the Luann. What can we use? And typically we would like to use well data, but there's very few well penetrations, and what we've got is not particularly useful. Seismic data. On most seismic data, we're lucky if we can even see the base of the salt, let alone any details on it. So what have we done? Well, around the edge of the basin, we've used 2D data. So this is a tracing that I made of a 2D seismic depth line on the edge of the Florida escarpment. And here in pink is the salt. And you can see how it goes from a basinal facies with diapirs to a marginal facies that has no diapirism, and it has a pinch out. So I've been able to map out, working with Maggie Curry a couple of years ago, we mapped out the pinch out edge, the marginal facies and the start of basinal facies on hundreds and hundreds of 2D seismic lines to produce this paleography for the Luann. There is the pinch out, the blue to gray. The marginal facies that we mapped is in pale blue, and we make this map. There's Florida, and I've rotated Yucatan back in. And what you can see here is interesting. It looks like geography. This looks like a flooded river valley or a ria. And this looks like a flooded estuary. And what I mean by that, so here's a ria, modern one, Sydney Harbour in Australia, the Parramatta, hard to pronounce, there you go, river. And this is what it seems to look like from our 2D mapping. So if we've got flooded river valleys during salt deposition, what was it doing before? Where were those rivers going? And there's two possible scenarios I can think of, end members. One is those rivers were flowing down into a basin that was hot and dry, and then they were evaporating, drying out some point down in that hot, dry basin. Another end member was that those rivers were flowing down into the basin, into a deep water lake full of water, maybe with some islands in. But based on what we had a couple of years ago, we just did not know the answer. Was it a hot, dry basin, or was there a big lake in the middle of the basin? But now we have some 3D data, which is actually giving us the answer. And the 3D data, thanks to TGS, is somewhere in this area. I cannot tell you exactly for confidentiality reasons, but suffice to say, it's on the Florida margin somewhere. And on these 3D data, we can actually see the edge of the salt beautifully imaged. So this is an amplitude extraction. You can see the salt in black and its edge against exposed basement here in white, beautifully developed and clearly imaged. And I'm going to blow up part of that and compare it. So this is above the top. That is the seismic mapping of the edge of the salt, salt in black, and the exposed basement and the edge in the pale colors. And you can compare this with a present day image of Lake Powell in the southwest US. Lake Powell is a flooding, drowned river valleys, and you can see the same shapes. This is at the same scale. You can see the same shapes and the same forms, like this peninsula here. Look, compare it to this one at the edge of the Luann. So again, this is giving us real good confidence that we're looking at drowned river valleys, incised river valleys that have been flooded at the base of the Luann. So here is a seismic example from that 3D. This is the top of the evaporites here. The bright, what you'll see is a white here. At the base of the salt is also very nicely imaged. Here it's this black, and you can see a lot of details on this line. So we can map out not just the top of the salt, but we can map out the bottom, and we can do a full interpretation of this in 3D, interpret it away to our heart's content, make a geological model like this, and we can make maps. So there was the area that we showed on the right, the top of the salt. Here is the map that we have made of the bottom of the salt, the structure. Let's zoom in on that in more detail. So you can see here now on the bottom of the salt, exquisite detail. Through here, there's a obvious meandering river system. It's got tributaries coming down through badland topography into it. Up here in this area, you can see a network of incised river channels coming together. You can see in this relatively flat plain area here, there are spiky high hills. So here's my interpretation of the drainage on that map. And I've given it names, and you can see here the big meandering river flowing off the edge of our data. And you can see these hills, or jabals is what they're called in North Africa and the Middle East. And there's a map of it. So an analog for this is the modern day Fremont River of, again, the American Southwest. And you can see here an incised meandering river with a system of tributaries with bad land erosion coming down into it. The whole thing is incised, even the meander system is incised. Now I'm going to compare that. This is the seismic data at the base of the salt, and rotate it round so you can see different aspects of it. You see here the big meandering river. You can see the tributaries coming down into it. You can see the roughness of the topography with the spiky hills sticking up out of the relatively flat plain area. So what this looks like very much is the sort of topography that is developed in modern day in Wadi Rum in Jordan and places like that. And I would love to go there. I have never been. And so we can go to Wadi Rum and get a good image of what this looks like. These are the angular jabals, or spiky hills of Wadi Rum. These are exactly the same scale, the same shape, the same texture even as the topography that we can map on the base of the salt. They typically have this form like pyramids, faceted pyramids with flatter plain areas in between. This is exactly what we're seeing on the seismic data. And here's another nice example of the same topography from a galaxy far, far away. So we've been looking at the details on this eastern part of the mapped area. And as I said, the big river unfortunately flows off our data. I'd love to see where it's going. Let's look at the other end, a detail in the other end of the data set. So we're going to be looking edgeways onto this. There's a high land in red and low in blue. Now let's look at it edgeways, and I'll rotate this round. So you can see the high land here. It's rough, it's fairly spiky. The low land, in contrast, is very, very smooth. Rotate it a bit more, we'll see some more details. You can see this roughness is erosive. These are erosional remnants. These are, in fact, this is a river network with river-cut canyons a few hundred meters deep. But on the other side here, the green region, a little deep further down, is smooth and completely different in texture. So because that was probably making you seasick, let's freeze that image here. And you can see the highland here, erosion cutting down into it. Here, the river systems are eroding with erosion controlled by the subcropping geology. And then they're forming a network coming down here, merging together until they reach this transition. And then the whole texture changes. There's rough surface topography with erosion, river-cut canyons up here. Down here, it's smooth. There's no erosion, there's no incision, and absolutely no evidence of rivers. There's a very sharp transition between these two textures, and it corresponds to a single depth level. We can even see more details in there, and I'll show you some examples of where we can identify what Jill has mapped out and identified as probable fan deltas. You can see arcuate failure and erosion back of the cliff margin of this body. So what is going on? Well, our interpretation is we're looking at something like this. This is a nice modern analog from Baja California, where we see the same sort of features, same sort of scale. Bedrock controlled erosional pattern here, incised canyons up to a few hundred meters with the occasional larger meandering river. And we do not see this bit on our seismic data, but we would love to see that. Now let's look at some actual cross sections. So from this area, A prime. A prime up here, the rough eroded relative highlands. And you can see these river cuts in here. Each of these notches corresponds to a mapped river. On each of the seismic lines that I'm going to show you, I've got a blue reference level, which is the same depth in each of these lines. The texture changes radically. Above the blue, it's rough and eroded. Below the blue, the surface, the base of the salt is smooth, and there's no evidence of erosion. Let's look at another line. Oh no, let's look at the interpretation. There you go. Smooth down here, rough and eroded. Here's another line, B to B prime through here. The transition from smooth to rough here is via a cliff, which appears to be fault bounded. There's the rough, eroded base of salt with the river cuts. Here, the smooth base of salt beneath the blue level. You can also see the stratigraphy beneath the salt. You can see how it's reflective and layered here with growth faults. And the youngest part of the system here has got a different facies. It's seismically transparent. It seismically does not contain layering and looks quite different underneath the smooth basin floor. Here's another line, C to C prime. The cliff face has grown as that fault has gained in magnitude. Again, same rough, eroded texture up here, transparent seismic facies beneath the smooth base of salt floor. Exactly the same depth cutoff at forming the transition between those two different textures. So here's our interpretation of that. And for once, I'm going to show you an example where it's easier to see what's going on without vertical exaggeration. So this is with 2:1 vertical exaggeration. Let's take that off. And what I mean here is you can see how the cliff face here that has been cut back with a cuspate erosion here, and that erosion retrogression stops at that level. And I'm giving away the answer here. What we think this is a lake, and that is the lake level. There is erosion above lake level. Below lake level, the lake floor is smooth. And on this data, this is where Jill has helped to identify and map out a fan delta of material that looks like it's actually come out from these notches. We interpret that this youngest transparent interval is probably clastic material, and it's probably time equivalent to the erosion surface that we're seeing up dip. So the model is something like this. We have a lake level. Above lake level, there is erosion cuspate cutting back into the fault-bounded cliff. Below the lake level, and starting precisely at lake level, is the top of a series of fan deltas building out from those. And then the water level appears to be consistent across this whole region, but it is not sea level. I'll come on to that later. It is below sea level. So that is the interpretation with the geological model. We have a lake. We can determine how deep that lake was. On this line, it's at least 1 kilometer, but this isn't the middle of the basin. So that lake was at least 1 kilometer deep here, could have got much deeper going into the middle of the basin. It's not at paleo sea level either. We'll come on to that later. At the end of this, so this is the pre-salt time. This whole landscape then flooded catastrophically. The water came in, and here is the Luann Sea, drowning the whole lot. And within the Luann Sea, we deposit the salt. So the Luann Sea covers both what was the land margin and the lake. And the salt covers both what was the land and what was the lake. So a final line here, with now, hopefully you're fairly familiar with this, rough, eroded level above paleo lake level, smooth basin floor. There's our fan delta building out, and the transparent material that we suggest is probably clastic material, equivalent in age to the erosion. So where is that transparent interval we're seeing in this region coming from? If it's clastic, the volume of clastics is way too big to be supplied by this local river system here. So we suggest that that large volume is actually coming down the big rivers. So the big river that we've mapped here on our seismic data coming into the lake, and probably other major river systems that we've mapped on the 2D data coming in from the southeast as well. So this is the pre-salt lake and pre-salt lacustrine clastics. I'm going to step back now. So we were looking just in detail at the left-hand end of this seismic line. Now looking at the whole thing. So this is where the paleo lake was, and you can see the topography of the base of the salt. And there's one of these jabals or desert hills that actually has salt over the top of it. And here's another jabal or desert hill, and this one, the salt did not cover the top of. There's various other indications of paleo horizontal and paleo level. Here is in the overlying Smackover formation. This is a carbonate platform. That tells us both the water depth relative to sea level, and it tells you what paleo horizontal is. The top of the salt is also a paleo horizontal. So we can take out the relatively gentle flexing of that line and restore it to its situation before it was flexed. So this is the area we were just looking at in more detail. This jabal or hill had salt over the top. This jabal did not have salt over the top. It was sticking out of the sea. The edge of the salt was here. So we can determine paleo sea level was here in the white line, and just before salt deposition, we had a lake in the middle of the basin, and we had a dry, exposed basin fringe like this. And I've taken the liberty of calling this, suggesting we call this lake, Lake Jackson, after Martin Jackson, the former leader of our group, who we greatly miss. At the start of the Luann time, the water came in and flooded this whole region. The Luann Sea covering the whole region up to paleo sea level. So we know now that Luann Sea was deep water, and we can determine in this area how deep it was. At the left-hand edge, it was about 2 kilometers deep. The Luann Sea, in which the salt was deposited, probably deepened significantly into the basin center. And we know that the surface of the Luann Sea was close to, or probably at, global sea level in the Jurassic. So there's our paleogeography now. And I have to say, it really does look like not just a subsurface map, but it really does look like a geography map. It's pretty realistic looking, because I think that is a real lost landscape. So we can now construct this model for what the pre-salt basin looked like. Rivers coming in, some of which we can map on these data, lacustrine turbidites in the basin, a deep lake, its surface about 750 meters below global sea level. Significance. Well, that base salt surface is a snapshot of the landscape, and it reveals those details with the incised rivers. We know that at least part of that pre-salt section is lacustrine. We suggest that that shallowest part, the transparent interval, is lacustrine plastics. When the water came in to make the Luann Sea, it flooded the lake, and it flooded the lake fringe, so the Luann lake waters are at least 2 kilometers deep. Final part of this talk. How long did it take to deposit the salt? What do you need to know? To calculate this, you need to know the thickness of the salt. You need to know, so its average thickness today, its average thickness at the time of deposition. You need to know how the basin was plumbed. Was the water coming in and flowing out at the same time, or was there some kind of one-way flow? Was it a basin that was being steady state, or was it cyclical drawdown? What was the composition of the brine coming in? What was the original water depth? We need to know that. And finally, we need to know the evaporation rate of the water. If you know all of those things, you can calculate how long it takes to deposit the salt. So let's do it. How thick was the original salt on average? That's a tricky question because the salt's very deformed. So there's a couple of approaches. This is one of my sections, present day, and you can restore these sections, the salt's in red, to get an estimate for the original thickness of the salt. Carl Fiduk has done a calculation using basically adding up the whole volume of the salt and redistributing it across the whole basin, and gets about the same answer. The original salt thickness on average was probably 2 to 3 kilometers average. So for our calculation, I've used this range with a mean of 2.5 kilometers and a range between 1 and 4. Next, was the basin depositing by steady state, as shown on the left here? The water comes in, the water evaporates, the salt deposits. Or on the right, a cyclical drawdown model. The water comes in, the water draws down and evaporates, you put a layer of salt down, and then you flood the basin again. Cyclic drawdown makes cyclic layering, what you call aciglio sequences. So you get cyclical carbonate, anhydrite, halite, sylvite, and it repeats carbonate, anhydrite, halite, sylvite over and over and over again. And these are very characteristic of cyclic drawdown. So do we see that in the Gulf? in the Luann. There is the Luann at the top, seismic data. It's really transparent. There's no layering, there's no cycles. There's nothing depositionally in it other than evaporite. No aciglio sequences. Compare that with the Santos. Here's the Santos. Beautiful image, and you can see these cycles of anhydrite, halite, sylvite, hundreds and hundreds of them. Very obvious. That is cyclical drawdown. We're not seeing that in the Luann. Here's the Zechstein from the Netherlands. Again, cyclical deposition of evaporite sequences. We don't see that. So we can determine it's not a cyclic drawdown basin. It's some kind of steady state. But is it being fed by one-way flow, the water comes in, or is it two-way flow, where water comes in and some flows out again? We really need to know that. So let's go back to the paleogeography. So Maggie Curry and me, we made this a couple of years ago, and you can map out the connection between the Luann Sea coming down through here towards the Florida Straits, the Luann Straits. We don't have that bit of data, but we've got it mapped down as far as here. So we can see that connection to the Southern Sea. It's mappable, it's extremely narrow, it's convoluted, and it's shallow. So it's a couple of 100 kilometers long. So you'd think through a narrow system like that, probably one-way flow. But let's put some hair on that model. So we know the approximate area of the basin. We can guess at the rate of evaporation. So we can estimate the approximate rate of water flow through the Luann Straits. And if we do that, the area times rate of evaporation ends up about 60,000 cubic meters a second of water has to flow through to keep the Luann Sea going. Compare that, it's about the same as the modern day Lower Congo River. So we now got a vision of what it looks like. And I've photoshopped the Lower Congo River here with the Red Sea hills at the top to give you a feel for what it looked like. So if you imagine a flow like this roaring through the Luann Straits, that's going to be one-way flow. Reflux is highly unlikely, which is great because that makes it a lot easier to calculate. Next question, what's the nature of the water coming in? So here's 3 computed box models. At the bottom, normal seawater coming into a kilometer deep hole. In the middle, water that's 5 times concentrated into the same hole, and at the top, water that's 10 times concentrated coming into the same hole. So let's see this race again. Okay, in comes the water, fill up the basin, and they're off. And straight away, 10 times brine is depositing salt, and it's full after 2,500 years. 5 times brine is coming up, it's reaching the finishing line, and it's finished. Meanwhile, normal seawater is barely out of the starting gate. And it's depositing relatively slowly. So we really, really need to know the concentration of the brine that's coming in. How are we going to get that? Let's think big. So here's a global, well, semi-global paleogeography. North America, South America, there's our Gulf of Mexico. And it's linked at the time through a series of ocean basins, through the Central Atlantic, the Galicia Basin, Neo-Tethys South Branch, and into the Neo-Tethys. Each of these big basins is connected with a constricted or choked link to the next one. And all of those basins lie in the arid tropics. So there's very little coming in the way of rainfall, very little coming in the way of rivers. So it's probably subject to net evaporation all the way from Tethys through to Gulf of Mexico. So we would expect it to be somewhat concentrated in brine. So I didn't come up with this idea. Tony Hallam, University of Birmingham, has been working on this concept since 1975, and he's published a lot about the mid-Jurassic basins and oceanography and climate. So let's look for some evidence how concentrated it was. This is looking at a plot of the anhydrite, well, basically calcium sulfate content. If you evaporate seawater, you produce an evaporite that is about 5% by weight gypsum plus anhydrite. If we look at the chemical measurements of the composition of the deep water Luann, it's about half that, just over 2% on average. You can't create the Luann salt by evaporating seawater. The Luann does not have enough calcium sulfate in. So where has all the calcium sulfate gone? Let's go back to our regional map. The easiest, most simple way to lose calcium sulfate is for this basin to have already got to the point where some way up the basin chain, it's already depositing gypsum and anhydrite, probably in this basin here. In which case, the composition of the water going into the salt basin, into the Gulf of Mexico, is probably at least 5 times concentrated relative to seawater. Could be 10 times. But there's a lot of uncertainty on this. So for our calculation, I've used this range, brine concentration relative to seawater. And I used a uniform distribution between 1 time and 10 times normal seawater, with a mean of about 5 times normal seawater. So we're getting there. We've almost got everything we need to calculate the rate. The final thing we need is the rate of evaporation. So let's go to the Dead Sea, because it's been very well studied. Dead Sea rate of evaporation, modern time, is between 1 and 2 meters a year of net evaporation. So that's a starting point for our rate of evaporation for the Luann Sea. But the Luann world was hotter and drier, and you were in the middle of a supercontinent. So it could have been evaporating faster. So I took the range that I'm going to use between of evaporation between 1 meter a year and 3 meters a year, with a mean of 2 meters a year, which is the mean is equivalent to the modern Dead Sea. Now we've got everything. So this is the inputs: net evaporation rate, the average salt thickness, the incoming brine concentration, and my estimate of the original water depth averaged across the basin. I used a 10,000 run Monte Carlo simulation to calculate the time to the end of salt deposition. And the answer is given here. The mode was 10,000 years to deposit all of the salt. The mean outcome was about 22,000 years to deposit all of the salt. So I don't want you to get too hung up on these numbers. What I do want you to take home is that it really does suggest that the time taken to deposit all of the salt, all of the Luann, was of the order of somewhere between 10 and 30,000 years. It's a very, very short space of time. So back to the toilet roll of time. The deposition of the salt does not fit in this scale, 20 million years. The deposition of the salt is equivalent to historical or archaeological duration, tens of thousands of years. Now that's a pretty radical thing for a major geological event. So now we get to conclusions. Deposition was very rapid, whichever way you cut it, tens of centimeters a year. At that rate, it's only going to take a few tens of thousands of years, maybe as few as a few thousand years, to deposit the whole of the Luann salt. That's really the blink of an eye. As far as I know, this is a challenge to everybody out there. I think that is the fastest rate of sustained steady state sediment deposition known to science. So not catastrophic, but steady state sediment deposition. If anybody knows of a faster sustained steady state deposition, let me know. But I think that is the fastest. So conclusions overall. Up till now, conditions of deposition of the Luann have been a mystery, but our 3D data reveals a spectacular buried landscape. We can see an arid land with rugged mountains, rugged hills, and incised rivers. we saw a large meandering river, all flowing into a deep pre-salt lake, which I'm calling Lake Jackson. The lake surface, 750 meters or so below global sea level at the time, in the pre-salt. When the basin flooded, the water came in through the Luann Straits and made a new Luann Sea, which was several kilometers deep. Luann deposition was very rapid, and my probabilistic modeling suggests it probably took a matter of only a few tens of thousands of years to deposit the whole thickness of the salt. So at that point, I'd just like to wrap up, thank everyone. My co-members of the AGL consortium group, the funders of our AGL consortium, particularly my co-author, Gillian Apps, and I definitely want to acknowledge Spectrum Data for initially providing us the data, and TGS. Thank you, TGS, for allowing us permission to show this presentation initially at the AUPG Salt Basins TIG. And with that, I will wrap up and open it to questions. Thank you very much.
All right, thank you very much. That was a very interesting talk. So the chat is open, so make sure to put your questions in there and your name and where you're from, and I will go through and read those to you.
Thank you.
I guess I'll just start it off with asking, have you looked at any cores to kind of confirm what you've gone through?
There aren't really any useful cores of the salt. People don't core the salt unless they do it by accident. So sadly, no. There isn't much in the way of useful outcrop either. So no, I have not looked at cores, and I've not been down any salt mines either.
All right, we're still waiting for the chat. So I'll ask another question. So the rapid deposition, do you think that attributed to the fact that there's no fossils in interlayered?
Definitely. There's two reasons why you don't see any fossils. One is the conditions were incredibly hostile to life. So you might have got marine creatures washed in through the Luann Straits, but nothing would be living in those waters. It's very low content of what's the word? Palynology, spores or whatever. So things blown in. It's low, very low density of those, which again would be consistent with very rapid deposition. Hope that answers the question.
Yeah. All right, we have our first question. Hi, Francis. This is Fatty Rad, and I'm writing from France. Thanks for your nice presentation. Just out of curiosity, aren't there any boreholes at which your salt basin to tie with the seismic data?
There are plenty of boreholes that allow you to tie the top salt to the seismic data. As I said, in general, people don't drill down to the top salt because the conventional exploration has been for sediments that are younger than the salt. So the deepest in general that people go to is the upper Jurassic Northlet, which is on top of the salt. There are a few wells that have gone through into the material underneath, but they tend to be right around the edge of the basin, and then they're not particularly useful for telling you what's going on in the middle of the basin. Around the edge of the basin, those wells typically find an anhydrite dominated sequence, but we know that the middle of the basin was halite dominated.
All right. The next question is from Graham Shields in London. Great talk. Did you use modern ocean composition for your estimates of how concentrated the brine was? Perhaps Jurassic calcium concentration or SO4 concentration was different?
That's a good question. Yes, I did assume that the calcium and sulfate composition of the seawater was equivalent to modern seawater. If anybody knows different, is there that the mid-Jurassic calcium and sulfate composition was different, please let me know. I haven't seen any evidence that it is different, but I likewise, I haven't searched for any evidence that it was the same. I wouldn't expect it to be that different, but I don't know.
All right. Next question is from Bill. He says, great talk. Being hundreds of meters below sea level, when did the ocean break through? Was it like a glacial lake outburst? Might you image large scale and high resolution bed forms? Or high energy bed forms?
Yeah, so we would absolutely love to see some data from the region to the south. I don't have any 3D data from there, and the 2D data that we have at UT does not extend any in detail further down. We would like to see it. Yeah, if you went to the southern part of the Florida margin, or the conjugate part of Yucatan, yes, you might expect to see something just like that. Because if you were looking at something of flow rates equivalent to the modern Congo River coming through and cutting a canyon, yes, we would expect to see some kind of evidence of that if you look in the right place. So far, we haven't seen it on the data that we've got, but like I said, we would want to look for that further south. We don't have the data there.
Next is from Douglas Watson at the University of Aberdeen. Have you looked at the pre-salt lacustrine stratigraphy of the South Atlantic salt basin, the Gabon or Congo? Very well imaged stratigraphy would be nice to compare to the transparent pre-salt package you described.
Yeah, I'm going to pass over to Gillian Apps to answer that.
Well, I have, yes, it's a different age stratigraphy, and I'm not quite sure whether there was a question in there other than that, but if there was, would he like to elucidate a little?
Yeah. So our problem has been that up till now, there's been no direct evidence as to what the stratigraphy under the salt in the central part of the basin consists of. The consensus in literature is, if you read the literature, things like Salvador's classic book, he talks about red beds and volcanics, and the assumption has been that it was a dry basin. But around the edges of the basin, there are certainly outcrops in the fringing regions where there is evidence of lacustrine deposition even within those red beds. But I'd be very wary about using anything around the edges of the basin as a guide to the conditions in the middle of the basin. So yeah, we would love to conjecture that the pre-salt lake was similar to what we see in the South Atlantic. That would be a very, very interesting outcome. But at this point, we are very, very early days for trying to make any kind of geological interpretation of what is going on beneath the salt in the middle of the basin. There are no well penetrations away from the very fringe of the basin. So it's all based on interpretation and model and science, really, rather than well data at the moment.
And relative to the size of the basin, we're looking at a very small part of it, but it's a critical step change in understanding to know now that it's a really very reasonable interpretation that we're dealing with a lacustrine setting prior to the global sea level being established for salt.
Yeah.
And that it's deep water.
Yeah.
The next question is from Eric Scott in Houston. How does this paleogeography interpretation modify our understanding of the deposition of the Norphlet Aeolian sediments?
Okay, Eric, that's a damn good question, a really important one.
Yeah, very.
So, one of the key questions. So, for those who don't have the Gulf of Mexico running through their veins, like Gillian and me and Eric, the Norphlet is what was deposited when the Luann Sea dried out. So the whole basin was a salt basin, then it dried out and you got desert conditions. And you have desert sands and sand dunes on top of the salt around the eastern fringe of the basin and probably around the Mexican fringe of the basin too. But nobody has found out what the equivalent was in the middle of the basin. So some people, like John Snedden, have said, okay, we'd like to use something like the margin of, where is it, the Namibia, as our analog for the Norphlet. So Namibia is on the coast, so there must be a sea. So there must be a sea in the middle of the basin. Other people have said, there are lots of analogs where you have sand fields around the edge of a sea. There is no direct evidence of that central sea at sea level. If we now know that the basin was deposited in a deep hole, the salt did not fill the basin to the brim. So when the salt deposition stopped and it dried out, the basin was below sea level. And so there cannot be a connection between the middle of the basin and the global ocean. So we know it was not a normal sea in the middle of the basin. So at the end of salt, it's quite possible there was a hypersaline lake remaining in the middle of the basin, or a series of hypersaline lakes, but it wasn't you weren't passing into normal seawater. That is very difficult to imagine. Yet you will see in a lot of publications, paleogeographies, where the middle of that Norphlet basin has got a normal sea in, and it just cannot work.
Right. Next question is from Morris in Bath. Amazing story. I suspect that most halite giants form at the same rate as yours. The Zeist and the Messinian in the deep med basins would be similar rates?
Yeah, so it's possible. I think there are differences. So the Messinian basin, we know, was fed by normal seawater coming through a gateway close to the modern Straits of Gibraltar. So we know that the water coming in was not pre-concentrated. So the rate of salt deposition in the Messinian is you couldn't have that sustained rate of equilibrium influx matched by precipitation. So what you see instead in the Messinian is a series of drawdown events, it looks like. So during the drawdown, yeah, deposition of the salt may have been as fast, but there were then long periods potentially of hiatus and desiccation before the next flooding event. I'm not an expert on the Messinian. I think there's another analog, potentially the Pre-Caspian basin, where again you can point at a chain of basins coming in that case from the north, and you see potentially the same segregation of the calcium sulfate from the halite. So again, the Pre-Caspian basin may be another case where you had very, very rapid salt deposited in steady state. But I think there's a big difference between cyclic drawdown basins and steady state basins. And the Luann is probably quite unusual because most salt basins seem to be cyclic. This one does not appear to be cyclic drawdown.
Graham Shields again. Previous estimates suggest that the Jurassic salt event was the largest in Earth's history, 2.4 kilometers cubed. Do you think this still holds?
Yeah, I do. I mean, I haven't changed the volume of the salt estimation. Something I would like to know, and maybe he or you or anybody else could answer me. I've not done the math to work out if you remove that much salt from the world ocean, what does it do to the composition of the remaining ocean? Does it make a significant difference to the salinity of the rest of the world sea? I don't know, but maybe somebody out there has done that calculation and can tell me. Well, I could probably do it myself, but I'm too lazy.
Excellent. Eric Scott again. How far west do you think the topography you have imaged extends?
Good question. We don't have seismic data, 3D seismic data going further west that shows anything like this quality of imaging. So like I said, over most of the basin, if you've got seismic data, you're really struggling to even see the base of the salt, let alone see any fine details on it. So we cannot tell. My expectation would be that there's a lot of the margin probably looks like this, but you simply cannot see it on modern day seismic data. I think this is a Goldilocks area where the depth is just right, the seismic acquisition was lovely, the processing was just right, and the overlying geology is just right for being able to see it. So we don't know for sure, but if you had a lake below sea level in the middle of the basin, in the far east of the basin, then there must have been similar conditions all the way around the edge of the basin.
Next question is from Jonathan at the University of Oslo. There have been reports of halite cement precipitation in Jurassic reservoirs. In the Barnett Sea, if it is precipitated during the Jurassic, you may be able to use information from the Barnett to better understand the seawater chemistry, if it's not too far afield conditions.
Yeah, that would be good. It's paleooceanographically a little different. For example, Jim Pindell has over the years made a very good case to show that during the Colovian, so somewhat later than the Luann, that the marine connection came in from the Pacific across Mexico. So it may be that the water that was coming into the Gulf of Mexico during the later Jurassic may have been not the same as the water that was coming in during the Luann, because the Luann, we think we got very good evidence for it coming in from the east. Jim Pindell's evidence is pretty strong that there was a connection later in the mid-Jurassic coming in from the west. But yes, it would be very interesting to look at those, at any information. It's always useful to compare and contrast. I have not done so.
Next question is from Nina in the Netherlands. Hello, and thank you for a fabulous talk.
Thank you.
Do you have any information or an educated guess or other consensus on the composition of the salt? Would it have changed through time?
So the composition of the salt, well, we've got good. There is a lot of data on that has been published. One of the problems is that obviously salt tends to be affected by dissolution. So we can see that in salt domes around the edge of the basin, a lot of the evaporite is modified, a lot of the halite gets removed, and you have relative concentration of the less soluble phases. And to an extreme level, on the top of salt domes, you get a cap rock where all the halite may be removed. So for the chemical composition, I focused on analyses of the composition from deep water penetrations, from deep water salt sheets, rather than from diapirs, because there is good reasons to assume that the evaporite would be less altered in those settings. However, the conclusion that it is deficient in calcium sulfate is using the present day, assuming that the present day in those deep water salt sheets is representative. If you assume that even the deep water is being modified by dissolution, that would say that the original evaporite was even more deficient in calcium sulfate. Yeah, we have to work with the data that we've got and the published. So we use published information from deep water wells because it's the least altered and the least likely to be altered. But there probably has been some chemical alteration by dissolution since the mid-Jurassic.
Next question is from Valentine.
Just quick before the question, Frank, your camera is off, just so you know.
Yeah, I'd frozen. So I'm just going to, can you see me now?
No.
No, okay. It must be an internet connection here. I can hear you. Don't worry about it. I'm ugly enough that you don't need to see me.
Okay. The next question is from Valentine in Oslo. I love the talk. So the deposition of the Luann was extremely short and didn't record any cyclicity, but you just mentioned that the top of the salt might have, correct? And could you match the cyclicity in the top salt, if it happened, to cycles recognized in the Aeolian neighboring sediments?
Okay, so we see, no, what we see is that at the top of the salt, it transitions from evaporite conditions to continental. So it's not so much a cyclicity that we see there as the end, the death of the salt basin. What we do see right around the fringes, rather than the top of the basin, is that there is a lateral transition and it becomes more anhydrite rich, right around in what would be the paleo shallow water. But we're not really, so I think the short answer to your question is no, you don't see a cyclicity that you can correlate with anything, because we really don't see any cyclicity at all.
Okay, Douglas Watson again. Do we really have the well calibration to say it's not cyclic? When you look at the wells in the Zechstein Red Sea South Atlantic, plenty of examples of transparent seismic with cyclicity still apparent in the logs.
Yeah, we have got enough information. I would say there are well penetrations with logs, so we can see that we certainly do not see within the middle of the basin major anhydrites within the salt. What we do see is that it looks like the conditions of deposition were right on the threshold between halite and halite plus sylvite. So there's a little bit of oscillation where you get layers which have a little.
All right. So yeah, thanks everybody for watching this week, and make sure to tune in next week to learn about submarine channel meandering. And thanks for attending.